Hello everyone, and welcome again to NEDL, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters for making this video possible, and would also greatly appreciate if you consider supporting us as well, so please check the link in the description for more details. My name is Sava, and today we're continuing to investigate various binary choice models that can be used to regress a categorical or a binary variable, that is, a yes or no variable, in a sense of a multiple regression model. In one of the previous videos, we have investigated the logit model, one of the most frequently used binary choice models, and its applications to credit scoring and predicting the probability of default of individual borrowers on their consumer credit. And today we're using the same example and the same real-life dataset to investigate yet another binary choice model, which is a close competitor of logit in terms of applicability and width of application, that is the Probit model. And the main difference we'll encounter today is that where the logit model uses the logistic distribution, as the name clearly suggests, the Probit model uses the more well-known and famous normal distribution. And Probit stands for probability. So prob is for probability, and it assumes that the errors of the forecasted probability are normally distributed and not distributed according to the logistic distribution. And for more videos on various probability distributions and how you can model distributions in case of various finance and economic applications, we have got the whole playlist for you to check out, so please do so if you are interested. But today we're interested in one particular application, the Probit model. So here let's investigate our dataset. We have got a dataset of 500 loan applicants that have been granted loans in the past by our bank, for example, and we have gathered data on their household characteristics that can predict their creditworthiness and whether they would repay our loan or not, and the outcome of whether they have defaulted on their consumer credit or not. So here we have got this binary variable that is of utmost interest that we aim at predicting, which is 0 if the borrower has not defaulted on their loan, if they have repaid it properly, in full and on time, and 1 if there were some ramifications, if they defaulted, if they didn't pay, if they couldn't pay, or if they chosen not to pay and ran away with the money. That is also a possibility. And here we can see that the sum of this variable, so the number of ones, the number of defaults in our 500 borrower sample, is 127, meaning that roughly 25% of our borrowers default, which is not a good figure, and we perhaps should aim at improving it, and that's why a credit scoring model that aims at predicting consumer defaults can be helpful. But it's also a good sign, as for a Probit model to be applicable, we need a non-negligible proportion of our binary variable being either 0 or 1. So here we have got quite a decent representation of both faithful borrowers and borrowers who defaulted, with defaults corresponding to, again, roughly 25% of our sample. If it was less than 5%, which is kind of a rule of thumb here, the Probit model and binary choice models overall would not be as precise, and they wouldn't have as much of a predictive power or statistical power in general, and you would have to resort to other techniques. But here we can stick with our Probit, or indeed with logit, as we did in the previous video. And here let's briefly survey the explanatory independent variables we have got to try and associate them with the likelihood of default. And as always, we have got just the constant, which always stays as 1. That's why it's called constant after all. Here we have got two explanatory categorical variables. Again, in a binary choice model, you need to have a categorical or a binary variable as your y, as your dependent variable, but your explanatory variable can be either a real number, just your usual numerical variable, or a categorical variable itself. So here we have got two binary variables, homeowner and full-time employed, that denote whether our borrower owns their property, owns their homes, and whether they are full-time employed. And here we can see that roughly half of our borrowers are homeowners, they own some property, and here we can see that more than half, almost 60% of our borrowers are indeed full-time employed. And we suspect that those would have a positive association with loan repayments and thus negative association with defaults. So homeowners and full-time employees would be less likely to default on their loans. And this is a hypothesis we can rigorously test using the Probit model. Here we have got some numerical variables of interest. First of all, we have got the data on income and expenses of the borrower's households in thousands of dollars per year. So we can see that this particular first borrower has an annual income of $129,000 per year, and they spend $73,000 of it every year. Here we can see that our average income across the sample is $161,000, so our households are quite wealthy, and they spend less than half of it. So we can see that they save quite a bit of money, and that's why we can expect that most of them would be able to afford their lending, and that's why we proceed to actually considering the applications in the first place. Here we can also see the assets and debt of these households before they have applied for a loan, and we can see that most of the households don't actually hold any debt as for now before they apply for the loan, and some of them hold some marketable assets that have quite considerable value. So this could be a predictor of repayment, as they can pledge these assets as collateral and thus alleviate our concerns that they might default. And last but not least, we have got the loan amount. The amount of the loan they are willing to take out from us, and we can see that this figure also varies quite wildly across our sample, and we can assume that the higher is the loan amount, the harder it is to repay it in full and on time. So we'll keep that in mind when designing our explanatory variables. And here are the three explanatory variables we can derive by modifying our raw data over here. So first of all, we can estimate how thrifty our applicants are by calculating the natural logarithm of the ratio of expenses to income. And the thriftier they are, the lower this number would be, and we would assume that the higher the expense to income ratio is, the less thrifty the household is, and the more likely they would be to default on their obligations. So again, we'll be able to rigorously test for this hypothesis when we get our Probit model coefficients. Then we can calculate the leverage of our household, just as we do calculate leverage of firms that we apply fundamental analysis to, perhaps. And here, let's calculate the leverage of those households after they have taken out the loan, assuming that they use the loan to fund purchase of some assets later on. So let's calculate the natural log of the debt after the loan is granted, so debt plus the loan amount. Obviously, this loan amount would be the outstanding debt of a borrower after we approve their application, divided by the assets of the borrower after we grant them the loan and they use it to purchase something, perhaps a home or a new car or something like that. So here we can see that the higher this value is, so the more leveraged our borrower is, the more likely we can suspect they would default, just as we do with companies. And then we need to also take into account how hard would it be in terms of income to loan amount ratio for our borrowers would it be to repay the loans in time. So here we can calculate the natural log of loan amount over income. So basically the logarithm of how many years would it take to repay the loan with their income. And that's all of the preparatory work we need to do in terms of our variables. So let's start specifying our logit model first. Here we have our coefficients for the constant and the 5 explanatory variables of interest, 2 categorical variables in terms of home ownership and employment, and 3 numerical variables that we've just derived using our raw data. And first, in the starting case, let's assume that all those coefficients are zeros, meaning that in the baseline case, we are not assuming any predictive power of any of those variables. In the Probit model, our probability, our main variable of interest that we then use to derive our probabilities, is the normal distribution that we apply to the combination of the coefficients and the variables to derive the z-stat. The z-stat can then be plugged into the standard normal distribution function to get the probability of default. So first let's calculate our z-stat using the sum product function and multiplying our coefficients, lock in the rows here as coefficient stays the same for all of our borrowers. That's the purpose of these coefficients, to be applicable to any borrower, and plug it in the values of the constant plus the explanatory variables for each and every borrower, and we don't need to log them as we want them to change from borrower to borrower, obviously. And we close the brackets and enforce this sum product formula, and then we can assess the probability by plugging that z-stat into the standard normal distribution. And we need to put 1 over here, as we want this function to be cumulative, to spit out probability and not probability density. So we're happy with that. And we see that by default, if we assume that none of these variables matter, and we cannot really discriminate in the statistical sense between borrowers based on their characteristics, the probability of default would be 50%. You couldn't do better than that if you have no insight into how these variables matter. You cannot really determine, and the best guess you can get is, well, coin flip. Heads, they'll default, tails, they'll not. And that's quite intuitive in the essence of a binary choice model overall. But how to optimize these coefficients? How to derive the optimal values of these parameters that maximize explanatory and thus potentially predictive power if we try and plug in our new loan applicants into this model and to assess whether they are creditworthy or not? Well, to do that, the most robust and rigorous way would be to maximize the log likelihood function. So we maximize the likelihood of the model fitting and predicting the defaults correctly for all of our applicants, for all of our sample observations, and to simplify computations, we do not maximize the product of all likelihood functions, but the sum of natural logarithms, using the property that a logarithm of a product of non-negative numbers, here probabilities are non-negative obviously, can be broken down as the logarithm of each and every of the product components. So here we can estimate the log likelihood for each and every of our observations, and then sum those values together to get the total log likelihood that we'll aim to maximize using Excel numerical solver function. So here we can use this formula to assess log likelihood, multiplying our y, so our dependent variable here, by the natural logarithm of the estimated y, so estimated probability over here, and adding 1 minus y, so the probability, the categorical variable that actually occurred, times the natural logarithm of 1 minus the estimated probability from the Probit model. And then we can bottom likelihood it all the way down to estimate these functions, these formulas for all of our sample observations, and calculate the total log likelihood that we'll aim to maximize using the sum function over all 500 borrowers. And now we can use the solver function to specify our optimization task to arrive at the best values of our coefficients possible. So we select cell L1 with our total log likelihood here, and we want to maximize it by changing the cells with our coefficients. So coefficients B0 for the constant and coefficients B1 through B5 for our explanatory variables. Now we need to untick this box to make some coefficients negative perhaps, as we do not really want to put restrictions on the coefficients. Some of the variables can exacerbate default probabilities and some can mitigate them. Some of the variables can make our borrowers more and less creditworthy respectively. And we need to stick with the gradient descent algorithm, as that's the best for log likelihood maximization over such quite simple conditions. So we can click solve and wait until the algorithm arrives at the optimal solution, and we see that our log likelihood has increased by more than 100, and it's now sitting at minus 233.5. And don't worry that this is negative. The absolute value of the log likelihood doesn't really tell you much. It's only in comparison to some other value that you can generate some inferences from it. But most importantly, we can look at our coefficients, and we see that our hypotheses have actually been fulfilled if you look at the magnitude of coefficients. Being a homeowner makes you less likely to default, as does being employed, with the magnitude of the employment effect being actually 3 times higher. And those parameters, leverage, propensity to expand your income, and the relation between the amount of loan and income, do increase the probability of default. So all the sanity checks have been passed. We do not get any weird results in terms of signs, at least. So let's now try and determine what the standard errors of those coefficients are, so we can test which predictors are the most significant in terms of identifying potential non-credit-worthy applicants, so we can then integrate it into our credit scoring model. So here, to calculate standard errors, we need to keep in mind one difference, one key point that differs the binary choice models from the usual multiple regression models. As you all know, the standard OLS multiple regression models assume homoscedasticity, that the variance of every single error term is the same. But here, judging from how probability behaves, the variance is actually different depending on the forecasted value of probability. And to account for that, we need to use the weighting matrix to arrive at our covariance matrix that we then can use to derive our standard errors of estimators. And that's what we've got down here. Our variance matrix would be the inverse of the product of the transposed matrix of explanatory variables onto the weight matrix and onto the usual non-transposed matrix of explanatory variables. The weight matrix is a diagonal matrix, so all elements besides the diagonal are zeros, and in the diagonal we have this expression that relates predicted probabilities and the square of the normal probability density function over the z-stat that we have calculated. So let's code our weight matrix and then proceed to derive our standard errors. So here we first need to check whether we lie on the diagonal or not. So if our row ID, and here we need to log the column, is equal to our column ID, and here we need to log the row, if they're equal, we do lie on the diagonal, and we need to input this particular formula. So let's input the standard normal distribution function over our z-stat over here, locking the column here as we don't want it to change as we drag it across and down, and input 0 over here as we want the probability density function and not the cumulative probability function here, square it, and then divide by the product of probability that we have estimated times 1 minus estimated probability. Columns locked throughout. And if we are not lying on the diagonal, the element of this weight matrix should be 0, as we do not assume any autocorrelation can jump into the picture, as those applicants are independent of each other. They are just randomly selected applicants from all applicants that have ever been granted a loan. So here, heteroscedasticity can be a problem, and that's why we're accounting for that using the weight matrix, but autocorrelation in such a cross-sectional binary choice regression should not be the case. So that's why we specify our weight matrix that way. We can enforce this formula, we can drag it across throughout all 500 by 500 array, and then use it to arrive at our covariance matrix for our coefficients, for our estimators. And here we can use the matrix algebra functions. So first of all, we need to calculate the inverse of a matrix, and the matrix that we want the inverse of is the product of matrices, so a mult. And first we input the transposed matrix of explanatory variables, including the constant, all the way through here. And then we need to multiply it by another product. First, we need to input the weight matrix that we've just calculated, and then we need to input the usual non-transposed matrix of explanatory variables. And we close the brackets again for the total product, close the brackets for the matrix inverse operation, and enforce this formula using Shift-Control-Enter, as this formula undoubtedly has a lot to do with matrices, obviously. And now, on the diagonal, we would see the estimators of the variances of our coefficients. So the square roots of these entries will give us our standard errors that we then can use to arrive at our well-known and appreciated z-stats and p-values that we can use to test for the significance of coefficients. So here, in this particular cell, the standard error for B0, for our constant term, let's calculate the square root of this particular entry, and then, to perform the calculations most efficiently, we can drag it across, and here increase the row number by 1, here by 2, here by 3, here by 4, and here by 5, so we correctly capture the square roots of all diagonal elements. And now the z-stat would just be the ratio between the coefficient and the standard error, and we drag it across, get z-stats for all coefficients, and now we can apply our two-tailed z-test, 2 times 1 minus the standard normal distribution of the absolute value of the z-stat cumulative to get p-values for all coefficients. And here we see that the constant is insignificant, which is not something we are entirely focused on, but the home ownership coefficient is insignificant, and that makes a difference, as we cannot reliably assume that home ownership is a decisive factor in determining probabilities of default, while these three factors, that is, being full-time employed, being leveraged, and having a high loan amount corresponding to the income, are the most significant, all three having z-stats higher than 3 in terms of magnitude, and p-values of less than 1%, signaling for high statistical significance. This coefficient, in turn, is marginally significant, only at 10% and not at 5%, but it still can be relied upon for our forecasts and predictions. And if we compare the results to the results of the logit model that we have estimated previously, we can see that the log likelihood is slightly lower for the Probit, meaning that logit is marginally more applicable to our dataset, but the difference isn't huge, so you can use either of the two or apply some other tests to figure out what's going on and which model to use ultimately. But in terms of the factors, we can see that the situation is very similar, with those three being very, very significant, and B3, which is expense to income ratio, insignificant in that case, marginally significant in that case. So not much of a difference if you look at p-values, but a lot of difference if you look at the significance threshold. And now finally, we can proceed with our analysis to determine how likely is some applicant out of sample to default. So assume some applicant approaches us and we survey them and figure out that they are a homeowner and they are full-time employed, and their household earns $150,000 per year, spends $120,000 of it, have $1 million in assets, and wants to apply for another extra $1 million in loan. So now we can actually just copy these across to arrive at the estimated probability of default given these. That stat estimated using the supplied values of the variables, and these calculated variables for expense to income ratio, leverage, and loan amount to income. And here we arrive at our probability, and expressing it as a percentage over here, we can see that the probability of default for such a borrower would be less than 20%, which could signal for their creditworthiness and inform our decision to grant the loan. And if we compare the prediction to that of a logit model, we see that is indeed very similar, signaling that the two models do have very similar output, at least in our case. And that's all there is for the Probit model and its application to consumer credit risk and credit scoring. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions for videos in business, economics, or finance you would like me to record. And please don't forget to subscribe to our channel or consider supporting us on Patreon. Thank you very much, and stay tuned.